Welcome to You Got Hope Chemistry. I'm Hope, and you're about to learn some chemistry. In today's lesson, we're going to look at two types of analysis, one called combustion analysis and the other one called hydrate analysis. Now, combustion analysis is how you can figure out the formula of a hydrocarbon by burning it. And hydrate analysis is figuring out how many waters are in a hydrated ionic compound. Now, both of these get tested quite frequently on the AP exam, and it really breaks down to stoichiometry. Again, this is all about mole ratios, because when we're trying to figure out a formula, we're essentially trying to figure out the number of moles of every type of element in the compound. So for instance, in a very basic combustion analysis, with just a hydrocarbon, which is carbon and hydrogen, this would be reacting with oxygen to produce CO2 plus H2O. Now, if we can know the initial mass of our hydrocarbon, and then through the experiment collect the mass of the products, it's possible for us to turn those masses into moles, and then those moles into mole ratios, which will eventually give us the values of X and Y in the hydrocarbon. So we're going to do one with a hydrocarbon, just carbon and hydrogen, and we're going to do one with a hydrocarbon derivative, which would have carbon, hydrogen, and oxygen, which will be much more difficult, but in general it's following a similar format. So let's start by getting right into a question. So the first question here says, cyclopropane is a substance used with oxygen as a general anesthetic. It contains only two elements, carbon and hydrogen. So I'm going to write this down. Carbon and hydrogen are in cyclopropane. And it says when 1 gram of this substance is completely combusted, so I'm going to say the mass here is 1.00 grams. And if we're combusting it, we're reacting it with oxygen. And it's producing, of course, carbon dioxide and water. So when 1 gram of this substance is completely combusted, so completely consumed, we know all of it is used up. That probably means that the oxygen here was in excess. We would produce 3.14 grams of CO2. And we would produce 1.29 grams of water. What is the empirical formula for cyclopropane? Now, the empirical formula from our previous lesson, remember, is the lowest ratio. So what we're actually going to end up finding out here is the lowest ratio, not necessarily the actual values. So for instance, this might come out as 1 and 3. But the actual molecular formula could be 2 and 6 or 3 and 9, any kind of increment increase of that, okay? Now, I'll talk about how I would actually figure out the molecular formula when we finish our basic calculations. All right, so what I want you to keep in mind in this question here is all of the carbon, which is in this hydrocarbon, has to end up in CO2. There is no other place where carbon exists. So we're going to use carbon dioxide to help us understand how much carbon we have in this formula. And very similarly, all of the hydrogen that's in this hydrocarbon ends up in water. So there's this connection between hydrogen and water, and there is a connection between carbon and carbon dioxide. And so that's where I'm going to start my calculations. I'm going to start by focusing on carbon, which is all in carbon dioxide. Okay, so I know the mass of carbon dioxide, and I know the mole ratio between carbon and 2 carbon dioxide. There's 1 carbon for every 1 carbon dioxide. So my goal is going to be to first turn this mass of carbon dioxide into moles of carbon dioxide. And then I can turn the moles of carbon dioxide into moles of carbon using a mole to mole ratio. So follow along and it'll make sense here. So let's start with that mass of carbon dioxide, 3.14 grams of CO2. So what I'm going to do is I'm going to turn this into the moles of carbon dioxide. Okay, so I know that there is 44.01 grams of CO2 for every 1 mole of CO2. What that does is it gets rid of the grams of CO2 and gives me moles of CO2. Now remember, all of the moles of carbon are tied up in this carbon dioxide. So I'm going to turn this into not moles of carbon dioxide, but moles of carbon, which will help me get this value of X. So for every 1 molecule of carbon dioxide, I have 1 carbon, right? There's 1 carbon in 1 carbon dioxide. So what this is going to do is convert those moles of carbon dioxide into moles of carbon, which is what we need to do to get this mole ratio in CXHY. So I'm going to take everything on top, put it in brackets, hit divide, take everything on the bottom in brackets, and hit equals. And this will give me a total of 0.07134 moles of carbon. Now I'm going to do the exact same thing, but I'm going to do it for hydrogen in water. Okay, so focusing on hydrogen, we know all of the hydrogen in our hydrocarbon got tied up into water. So starting with water's mass, it's 1.29 grams of H2O, and I need to turn that into moles of H2O. So for water, it's 18.02 grams of water for every 1 mole of water. So what that's going to do is give me moles of water. Now what I want to do is turn that into moles of hydrogen. So for every 1 mole or molecule of H2O, I have 2 moles of hydrogen. So the moles of water are going to cancel out, and I'm left with moles of hydrogen. Now if I take everything on top, I hit divide, everything on the bottom, hit equals, I get a value of 0.1432 moles of hydrogen. Now, essentially what I've come up with is this concept of C is 0.07134, H is 0.1432. Well, that looks really weird. We need to get these into whole numbers. So I'm going to do this by dividing the number of moles that I've calculated by the lowest of the 2 values. So between this value and this value, the 0.07134 is the smallest of the 2 values. So I'm going to divide both of them by that value to get my number of moles in a whole number. So if I divide this by 0.07134, I'm going to get 1 mole of carbon. If I divide this by 0.07134, I'm going to get essentially 2 moles of hydrogen. So what I've done by dividing by the smallest number is I've turned this weird looking thing into C1H2. That is the empirical formula for this hydrocarbon. Of course, we normally don't put the 1 there, but I'm just doing that to highlight it. Now, I want to talk about the molecular formula. The molecular formula is the actual number of carbons to hydrogens. There is nothing, no hydrocarbon that is 1 carbon and 2 hydrogens. It does not exist. So you would have to be given some extra information to figure out what the molecular formula is. And I'm going to give that to you now just because it's part of organic chemistry, which we haven't covered. Prop here in cyclopropane, prop stands for 3 carbons. That's what it means in organic chemistry. So I know that this is actually C3, And if the ratio is 1 to 2, then hydrogen here must be double 3, so it's C3H6. This is actually what the formula is for cyclopropane, and it actually looks like this. It's 3 carbons in a triangle, and each carbon has 2 hydrogens coming off of it like that. Okay. There is a lot of strain in this molecule, and so it's not super stable due to the very tight bond angles in this triangle. In our next question, we're going to be looking at a compound which would be called a hydrocarbon derivative. It contains oxygen as well as carbon and hydrogen. So these questions take about twice as much work to complete. They are a little bit more difficult, but the generic way of how we started the previous question still holds true. So let's read the question, and we'll write out the theoretical equation and fill it in to the best of our ability. So it says, when caffeic acid is analyzed by combustion analysis, a 0.300 gram sample produces this much carbon dioxide and this much water. Caffeic acid contains only carbon, hydrogen, and oxygen. What is the empirical formula? So again, the empirical formula is going to give us the lowest ratio of carbon to hydrogen on oxygen, not necessarily the number of carbons, hydrogens, and oxygens in the actual compound. That would be the molecular formula. So let's start with this. We know it contains carbon, hydrogen, and oxygen, so I'm going to call it X, Y, and Z. The X, Y, and Z is the number of moles of each of these. So ultimately, our goal is to get the number of moles of carbon, hydrogen, and oxygen in order to get the values of X, Y, and Z. So we're going to be reacting that with oxygen. It's still only producing CO2 gas and H2O gas. Now, it says we are starting with a mass here of 0.300 grams. The CO2 has a mass of 0.6595 grams, and the water has a mass of 0.1200 grams. So before I kind of start, I want to lead you through how to solve it just verbally. Now, there's oxygen everywhere, okay? So there's oxygen in all 4 of these compounds. However, the amount of carbon that is in this hydrocarbon derivative all ends up in carbon dioxide, just like our previous question. All of the hydrogen in this hydrocarbon derivative ends up in water. It all gets there. I know that all of the mass ends up there. The tricky part is really the oxygen. However, if we were able to figure out the number of moles of carbon in here, the way we did in the previous question, if we figured this out first, we could then use the molar mass of carbon to figure out the mass of carbon. And if we figure out the number of moles of hydrogen, like we did in the previous question, we could then use the molar mass of hydrogen to get the mass of hydrogen as well. Now, if I had the mass of hydrogen and the mass of carbon, I could subtract those away from the mass of this compound, which would then give me the amount of mass of oxygen in that compound, and therefore I would then be able to calculate the moles of oxygen, which would give me my mole ratio. Now that might sound confusing, but I wanted to give you a general picture before we get too locked up in kind of making calculations. So again, this here is an additional step we're going to have to do compared to the previous question. And the reason why we're getting these two masses is that if we take the mass of this compound and we subtract away the mass of carbon and we subtract away the mass of hydrogen, we're going to end up with the mass of oxygen. Once you have the mass of oxygen, you can get the moles of oxygen. And if we have the moles of oxygen and we have the moles of carbon and we have the moles of hydrogen, we can get the lowest ratio of those three elements. So let's begin, starting with carbon. All right, we have 0.6595 grams of carbon dioxide. I need to turn that into moles to get the number of moles of carbon. So there are 44.01 grams of carbon dioxide for every 1 mole of carbon dioxide. That is simply the molar mass. This will get rid of the grams of carbon dioxide. Then I need to convert this into moles of carbon. Well, there's 1 mole of carbon, or 1 carbon, in every 1 mole or molecule of carbon dioxide. This is looking very similar to our previous question. The CO2 cancels out. And we are going to calculate this. We're going to get a value. So everything on top, hit divide. Everything on the bottom, hit equals. And we end up with 0.01498 moles of carbon. So I'm going to put that up here, 0.01498. Now I have one more step to do though. I need to turn this into mass of carbon, and I can simply do that with the molar mass of carbon. So I can say that there is 12.01 grams of carbon for every 1 mole of carbon. This will give me the total mass of carbon in the question. So punching that into my calculator, I would get a value of 0.1799 grams of carbon. Now I'm not rounding anything here. I'm keeping all of my digits right to the end of the question. So I'm going to put that up here. This is 0.1799 grams of carbon. All right, we now need to do the exact same thing for hydrogen using water. So for hydrogen, we have 0.1200 grams of water. I need to turn this into moles of water using molar mass. There's 18.02 grams of water for every 1 mole of water. The grams cancel. I'm left with moles of water. I now need the moles of hydrogen, so I need to multiply that by the molar ratio. Well, there's 2 hydrogens in water, so 2 moles of hydrogen for every 1 mole of water. The moles of water cancel out like this. I take everything on top, I hit divide, I take everything on the bottom, I hit equals, and I punch it in my calculator. This gives me a value of 0.01332 moles of hydrogen. So again, I'm going to go to the top of my page here. I'm going to place this in here. I have 0.01332. I have to figure out the mass of hydrogen though in order to figure out the mass of oxygen. So for every 1 mole of hydrogen, it weighs 1.01 grams. So typing that into my calculator, I get a value of 0.01345 grams of hydrogen. Okay, so I'm going to bring that up here, 0.01345 grams. What we have done by doing this green step is I have now figured out the mass of carbon. I figured out the mass of hydrogen. We have the mass of the compound. If I subtract the carbon and hydrogen away from the compound, I'm going to be ending up with the mass of oxygen. So let's do that down here. Let's focus on oxygen. So the first thing we're going to do is we're going to get the mass of oxygen. We're simply going to take the mass of the compound, 0.300 grams. I'm going to subtract away the mass of the carbon. I'm going to do it in green so it matches, so minus 0.1799 grams. We're going to subtract away the mass of hydrogen, 0.01345 grams. And when I put that in my calculator, I come out with a mass of 0.1066 grams of oxygen. So I got the grams of oxygen, but I need to have the moles of oxygen to compare the moles of the 3 elements to one another. So another step we have to do is now convert this into moles of oxygen. So using the molar mass of oxygen, I know that there is 16.00 grams of oxygen in every 1 mole of oxygen. Now, if I type that in my calculator, I get a value of 0.00666 moles of oxygen. All right. So I have my 3 sets of moles that I need to get the numbers of X, Y, and Z. I have moles of carbon. I have moles of hydrogen. I have moles of oxygen. What I simply have to do is figure out which of these is the smallest value and then divide all of these values by that number. So the smallest of those numbers is the 0.00666. Okay, so for oxygen, that's going to give us 1 mole of oxygen. If I divide that by hydrogen, 0.00666, I'm going to get a value of 2. If I divide this by 0.00666, I'm going to get 2.25. So right now, what I have is this: carbon, 2.25, hydrogen, 2, oxygen, 1. So what I'm going to do is I'm going to constantly multiply these by a value till I make everything a whole number. So for instance, if I multiplied this by 2, it'd be 4.50. That's not a whole number. So I'm going to try 3. So then I multiply it by 3, and that's not going to give me a whole number. But if I multiply this whole thing by 4, I'm going to get a whole number ratio. That would work out to C9H8O4. This would be my empirical formula. It is the lowest ratio of carbons to hydrogens to oxygens. So I'm not saying this is the formula. I think it probably is, but it has to be some kind of increment of this. It would have to be multiplied by 2, so C18H16O8, or I'd multiply it by 3, or I'd multiply it by 4. The only way I would know which formula I have right is if the question told me the molar mass of caffeic acid. I could then compare it to the different ratios and confirm the actual formula. The next thing we're going to look at doing is an analysis of a hydrate. Okay, so a lot of people don't understand what a hydrate necessarily is, so I'm going to start by making sure that we have an idea of what a hydrate is. I'm actually going to give you the answer to this question. We're going to proof it after, but probably the most common hydrate you come across in high school is copper 2 sulfate pentahydrate, so 5 waters. So what happens is this: if I dissolve copper 2 sulfate in water and I allow it to just evaporate naturally at room temperature, not all of the water will escape the crystal lattice. So copper 2 sulfate itself is actually a white powder, but copper 2 sulfate pentahydrate is a blue crystal. So as water naturally evaporates from the solution, a ratio of 1 copper 2 sulfate formula unit basically hides 5 waters within the crystal. So the analogy I always give is when I chew gum, the gum is in me, but it's not really part of me. And so when the solution evaporates, 5 waters get trapped in the crystal lattice per copper 2 sulfate. The waters really aren't part of the ionic compound, they're just trapped inside of it. So what our goal is going to be is to figure out, how do we know how many waters are trapped in an ionic crystal lattice hydrate? So the way you would do this in the lab is you would weigh out a sample of your hydrate. You'd take the mass of it initial, and then you would heat it up in a crucible using a Bunsen burner. And when you heat up the hydrate, what happens is it drives off the water. This will evaporate off. And so the compound is going to lose mass. So this is going to be a larger mass. This value here is going to be bigger. And then you would weigh it again. So I'm going to call it final 1. Okay, you'd weigh it, and then you would heat it up again, and you would weigh it. And you would heat it up again, and you would weigh it until these values become very, very constant. Then you know you've driven off all of the water. And if you've driven off all of the water, then you can figure out the mass of water that is left. And if you know the mass of water that left, you can figure out the moles of water. And this is a mole-to-mole ratio. This is 5 moles of water to 1 mole of copper 2 sulfate. So the goal here again is always calculating moles. Moles, 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 moles. Moles are our friend in calculations. So let's try the question below. It says, samples of the following hydrates are weighed, heated to drive off the water, like I explained, cooled and re-weighed multiple times until a constant mass is achieved. Calculate these values of A through C. The first one we're going to figure out that value of A. It's going to come out to 5, but I need to show you how this is possible. Okay, so we have a couple of numbers given to us so far. We have the mass of our hydrate. So CuSO4 times 5H2O. This is 8.69 grams. We know the mass of the residue. The residue is just the ionic compound because it doesn't evaporate, only the water evaporates. So we know the mass of copper 2 sulfate is equal to 5.56 grams. So what we need to know now first is, what is the mass of water? Because if we know the mass of water and we know the mass of copper 2 sulfate, we can turn these into moles. And then we have a mole-to-mole ratio, which would represent the coefficients in these compounds. So let's start with figuring out first the mass of water. So to figure out the mass of water, I have to take the mass of the hydrate, 8.69 grams, and subtract away that water mass, the copper 2 sulfate mass of 5.56 grams. And if I do that, I will get a mass of 3.13 grams of water. So let's put that in here. This is 3.13 grams. Now that's all that's left to do, is to figure out the moles of copper 2 sulfate and figure out the moles of water and divide by the smaller of the two values. So let's start with the copper 2 sulfate. So let's get now the moles of CuSO4. So starting with the mass, we have 5.56 grams of CuSO4, and we need to multiply that by 1 over its molar mass. So the molar mass is 159.62 grams of CuSO4 for every 1 mole of CuSO4. The moles of the grams cancel out, and I'm left with moles, and the number of moles is 0.03482 moles of CuSO4. I am not rounding anything at this point. Okay, we now need to do the same thing, but we are going to do it for water. So the moles of water. So we have 3.13 grams of water. I need to turn that into moles of water. There's 18.02 grams of water for every 1 mole. The grams cancel out with the grams, and I'm left with a value of 0.17369 moles of water. Now, the number of moles of water, this should always be the bigger of the two values or equivalent. We never have a number larger than 1 in front of the ionic compound. It's always a 1 to 2, 1 to 3, 1 to 4, etc. ratio. So what I need to do is divide everything by the smallest value. And the smallest value of the two, of course, is this one here. I'm going to divide this by 0.034832, which is going to give me 1. I'm going to divide this one by 0.034832. And when I do that, I get a value of 4.99 something something. It is so close to 5. I'm assuming that this is 5. So now I know that it is 1 CuSO4 dot 5 H2O. So what I would like you to do at this time is pause the video and try to figure out the value of B in this question. So looking at this question, we are beginning with the same two types of information. First of all, we have the mass of the hydrate. So this is a cobalt 2 chloride hydrate. This one is a reddish pinkish color, depending on how concentrated it is as a solution. As a crystal, it's quite red. It's 11.73 grams. We have the mass of the residue, which is the ionic compound of CoCl2. So that's 6.41 grams. We can use this to figure out the moles. But what we need to do first is figure out the mass of water. And we're going to do that by taking the mass of the compound total minus the mass of the ionic part of it, so 6.41 grams. And if I do that, I get a mass of 5.32 grams of water. So that's my mass of water, and I now need to turn that into moles of water. All right, let's start with our ionic compound. So I'll start with our CoCl2. So I've got 6.41 grams of cobalt 2 chloride. The molar mass of cobalt 2 chloride is 129.83 grams for every 1 mole of CoCl2. And the grams will cancel. And if I do this calculation, so 6.41 divided by the 129.83, I get a value of 0.049372 moles of CoCl2. Now we have to do the same thing for water. So we figured out the mass of water, so we take the 5.32 grams of water, we multiply it by 1 mole of water over its mass, 18.02 grams of water. The grams will cancel, and I'm left with moles, and the moles of water is 0.2952 moles of H2O. Now, the next thing I'm going to have to do is divide by the smaller of the two numbers, which of course is always going to be the ionic compound value. So I'm going to divide this by 0.049372, which will give me a value of 1. I am going to divide this by 0.049372, and that's going to give me a value of 5.979, which I'm going to assume is close enough to 6. So the hydrate value would be 6. This would be 1 CoCl2, that 1 is coming from up here, dot 6 H2O, with the 6 coming from here. I hope you have enjoyed this lesson of You Got Hope Chemistry. See you next time.